Okay, so welcome back to the Deep Dives, and today we're going to be tackling something that I think is probably on a lot of people's minds right now working in the field. It's basically this problem that compute keeps growing faster than our supply of really good high-quality text data.
Yeah.
This data bottleneck. It's a huge hurdle for AI progress, and it's definitely something that I think about every day.
Yeah, no, absolutely. And we've seen incredible leaps in capability, just from scaling up model size. But the strategy, it really is fundamentally tied to having, bigger and bigger data sets.
Right.
And so if we hit a wall with data quality or, just the sheer cost of curating these massive data sets becomes unsustainable, we really need to think about, new approaches to keep pushing the boundaries of what LLMs can do.
Yeah, and so that brings us to the paper that we're diving into today. This is Reasoning to Learn from Latent Thoughts by Ruan et al. From 2025. And the idea here is actually, I think, quite elegant. Instead of just throwing more data at LLMs, can we make the data that we already have, way more informative?
Yeah, and I think what's so interesting about their approach is the intuition behind it. The idea that when humans generate text, especially when we're explaining complex topics or working through problems, there's a detailed internal reasoning process, right? Like a series of latent thoughts that eventually leads to, that final written output. And so from that perspective, web text could be seen as a compressed end product of a much richer cognitive process.
Right, exactly. Like think about it, even for yourself, when you're developing some complex algorithm or outlining a research paper, you don't just instantly produce the final polished version, right?
Right.
There are intermediate steps.
Yeah.
There's exploration of different ideas, maybe some internal trial and error. And this paper is saying, hey, those latent thoughts, those hold critical information for learning, information that we're just completely losing when we only train on the final condensed text.
Yeah, and so the researchers set out to kind of enhance the data efficiency of LLM pre-training by explicitly modeling and inferring these latent thoughts. So their core hypothesis is that if we can train an LLM not just on the text itself, but also on a model of the reasoning that likely generated it, we can achieve, much better performance even with less raw data.
So how do they do this? What's the approach?
Yeah, so they explore a couple of really neat methods to achieve this. So the first involves using synthetic data. So they take a math data set called Fine Math, and they employ a really powerful teacher model. So think, like a highly advanced iteration of GPT-4. And they use this to try to reconstruct the latent thought processes that could have led to the solutions in this data set.
Oh, so they're kind of saying, let's have a really intelligent model show its work step by step, even if those steps weren't explicitly written down, the original training data.
Exactly.
So, interesting.
And so this synthetic data enriched with these inferred latent thoughts is then used to augment the raw training data for a smaller LLM, specifically Tiny Llama 1.1b.
Got it. Okay, so what kind of results did they see?
Yeah, so the results were actually quite remarkable, especially in a data-constrained domain like mathematics. So on the math benchmark, the model trained with this latent thought augmentation achieved a really impressive 25.4% accuracy.
Wow.
And to put that in perspective, a model trained on the same amount of raw fine math data only reached 5.74%.
Oh, wow.
So that's a pretty substantial leap in performance.
Yeah, that's huge.
And importantly, they benchmark this approach against other data augmentation strategies, including one called RAPCOT, which stands for Rephrasing the Web with Chain of Thought Reasoning. And while RAPCOT did provide an improvement over the raw data baseline reaching 19.4% accuracy on math, it still significantly lagged behind the latent thought augmentation. And you can actually see this comparison pretty clearly illustrated in Figure 6 of the paper, which presents the accuracy results on both the math and GSM 8K benchmarks for these different training methods.
Okay, so it sounds like they're not just getting higher overall accuracy scores, but also like this latent thought approach is making the model more resilient to variations in how it's prompted.
Exactly.
For Q-shot chain of thought reasoning. So even when the phrasing of the prompts was altered, the models trained with latent thoughts maintained their performance better than the baseline models. I mean, that's a pretty big deal, right? Because it suggests a deeper, more fundamental understanding is being developed.
Yeah, I think that's a really critical point for us, as practitioners, that if a model's reasoning capabilities are more deeply ingrained by learning from these latent processes, it should be less sensitive to, the precise wording of a prompt.
Right.
And Figure 8.2 in the appendix provides some good visual evidence of this robustness across different prompt styles.
Cool. And I also saw that they achieved this enhanced performance even when the model was exposed to the raw data fewer times.
Yeah. Yeah.
So figure 8.3 shows that when you normalize performance by the effective number of raw tokens, seeing the advantages of their method become even more pronounced. So it seems like it's not just better, it's also more efficient.
Yeah, it really underscores those data efficiency gains. So,
Right.
this initial part of the paper provides strong evidence that explicitly incorporating something akin to the thinking process into the training data can be a really effective way to boost an LLM's reasoning abilities, particularly when dealing with limited data. But what's perhaps even more groundbreaking is their second major contribution.
Oh, okay. And what's that?
So this is called Bootstrapping Latent Thoughts, or BOLT. And here they push this concept of latent thoughts even further. So they investigate whether an LLM can actually learn to improve by generating and learning from its own latent thoughts without the need for that powerful external teacher model like the advanced GPT-4 variant we talked about earlier.
Oh, well. Okay, so the student becomes the teacher.
Exactly. And BOLT is formulated as an Expectation-Maximization, or EM algorithm. So this is a technique commonly used in machine learning when we're dealing with these unobserved or latent variables. And figure 5 in the paper has a really nice visual representation of this iterative process.
Okay, so let's break down this EM algorithm. So the E step, or expectation step, involves using the current iteration of the LLM to infer the latent thoughts that might underlie the existing training data. But it's not just about making a single best guess.
Right.
They use Monte Carlo sampling, essentially generating multiple plausible thought processes for each piece of text.
Yeah, you can think about it as the model exploring different potential reasoning pathways that could have led to, that observed text. And by taking multiple samples, denoted as K samples in the paper, they can obtain a better approximation of the true underlying reasoning, a tighter bound on the posterior distribution of these latent thoughts.
Right, so the more samples they take, the more refined this approximation becomes.
Exactly. And this is what they refer to in the paper as a policy improvement operator, because it aims to obtain higher quality latent thoughts.
Okay, and then after this, you have the M step, the maximization step, where the LLM is trained again. But this time on the original raw data, augmented with the synthesized latent thoughts that were generated in the E step. So now the model's learning not just from the text itself, but also from its own best attempts at, reconstructing the reasoning behind that text.
Exactly. And so this is where that self-improvement loop really kicks in. The idea is that the model trained in the M step is now more capable.
Right.
And consequently, in the subsequent E step, this more advanced model will be able to generate even better, more insightful latent thoughts. And then this higher quality, thought augmented data then leads to further improvements in the M step, and the cycle repeats. It's like the model is having this internal dialogue, constantly refining its own understanding.
So yeah, like it's bootstrapping itself up.
Oh.
So they actually explore two different setups for this bootstrapping process, right?
That's right.
So the first is bootstrapping on fixed data. So that means taking a single training corpus and retraining the model from scratch in each iteration using that same data, just augmented with those increasingly refined self-generated latent thoughts.
Exactly. And Figure 7a illustrates this setup, and this allows the researchers to really isolate the specific impact of the improved latent quality.
Okay, so looking at the results from this fixed data bootstrapping experiment, we see consistent performance gains on the math benchmark across those iterations,
Right.
along with improvements in likelihood metrics. So it definitely seems like the model is learning and becoming better at generating these useful latent thoughts.
Right, exactly. And Figure 1 on the right also kind of visually summarizes this iterative improvement in math accuracy.
Okay, and then the second setup is what they call continual bootstrapping, which feels a lot more aligned with how we actually train these models in the real world.
Yeah, for sure.
So in this case, as we can see in Figure 7b, the model continues its training and updates its latent thought generator as it processes, larger and larger portions of the training data throughout these bootstrap iterations.
Right. And Figure 11 shows those results for continual bootstrapping. And again, we see consistent performance improvements in both likelihood metrics and downstream math accuracy as the bootstrapping process unfolds. And what's really interesting here is that they compare it to scenarios where they fix the latent generator at an earlier iteration, and the models undergoing continual bootstrapping, they show a much steeper upward trend.
Okay.
Suggesting that continuously improving the latent thought generation mechanism is really crucial.
Yeah, I mean, that makes a lot of sense. So it seems like they're getting these pretty good results. Are there any limitations to this approach?
Yeah, so, as with any groundbreaking research, it's not without its challenges and limitations. And the researchers do discuss some potential side effects. So, one notable observation was a decrease in few-shot GSM-8K performance over successive bolt iterations. And this is shown in figure B.5. So that's, potentially a concerning trade-off.
Right. So is there any way to mitigate this potential for like over-specialization without losing the gains in reasoning on tasks like math?
Yeah, so their hypothesis is that the continuous pre-training on the math-heavy fine math corpus might be negatively impacting the model's more general natural language understanding capabilities, which are really essential for, interpreting the word problems in GSM-8K.
Right.
And the results on the DCLM validation set presented in figure B.5 on the right seem to support this idea, showing a decline in negative log likelihood on a general domain dataset as the model is trained more extensively on fine math.
Makes sense.
And Appendix D.4 also provides some insightful failure examples where the bootstrapped models appear to kind of misinterpret the nuances of the math word problems. So it highlights, this key challenge of ensuring that gains in one area don't come at the cost of regression in others.
Right. It's a good reminder that even with, these really cool new techniques, we have to be careful about unintended consequences and the potential for models to become overly specialized in a way that hurts their performance on other important tasks. So are there any other limitations?
Yeah, so the researchers acknowledge that their initial exploration of design choices in this study is somewhat limited. There are a number of avenues for future investigation, like experimenting with different generative structures for the latent thoughts themselves, exploring various warm stir data strategies or more advanced sampling techniques like sequential Monte Carlo. And carefully tuning the different hyperparameters involved. So these are all areas where further research could lead to, significant improvements.
Yeah, and of course, a general concern when dealing with any form of self-generated data is the potential for amplifying existing biases.
Right.
If a model starts learning from its own potentially flawed or biased thoughts, that could lead to a compounding of these issues as the bootstrapping process continues. That's definitely something that needs careful consideration in future work.
Absolutely.
So beyond just the pre-training phase, the paper also touches upon the really exciting potential for these models trained with latent thoughts to actually exhibit, enhanced reasoning abilities on downstream tasks. So figure 4 and Appendix D.1 show that these models can be effectively few-shot prompted to perform chain-of-thought reasoning within the latent space on tasks like math.
Yeah, it's really cool. So instead of simply generating a final answer, they can be guided to think through the problem step by step in this inferred thought space.
Yeah, and the examples provided in Appendix D.1 covering areas like algebra, combinatorics, number theory, and math word problems really underscore this potential benefit that extends beyond just improving the initial pre-training.
Right.
So where does this work fit in with all the other exciting research that's going on in AI right now?
Yeah, so when we consider how this work fits into the broader landscape, we see, clear connections to other efforts focused on synthetic data generation. Such as the work by Eldon and Lai with Tiny Stories or Gunasekar et al. Textbooks are all you need. And there are also links to paraphrasing-based data augmentation techniques like WRAP, although as the paper itself points out, their unique latent variable perspective and the iterative bootstrapping aspect really set their work apart.
So it seems like it's kind of building on some of the, the recent trends of, synthetic data, and also this growing understanding that large language models seem to possess these like hidden reasoning capabilities.
Yeah, absolutely.
That we're only starting to, uncover and explore.
Yeah.
So to summarize for our listeners, many of whom are probably working on these problems themselves, what are the key takeaways?
So I think, this research really suggests that explicitly modeling and inferring latent thoughts represents a promising and potentially transformative direction for significantly improving data efficiency in LLM pre-training.
Right.
Particularly in data-constrained domains like mathematics, where reasoning is paramount.
Yeah, we saw nearly a 5-fold increase in accuracy just by teaching the model how to think, even with the same amount of raw data.
Exactly.
That's a huge efficiency gain, which could be a real game changer.
Exactly. And then, the introduction of the Bolt algorithm unveils this new self-improvement mechanism where LLMs can iteratively refine the quality of their own internal thoughts, leading to consistent and measurable performance gains. And, the finding that scaling inference compute during this thinking phase further amplifies these improvements is also a critical insight.
And all this is happening, even though, this is still early stage research. there are limitations and potential side effects that need to be investigated.
Yeah.
But the fundamental concept of leveraging the inherent reasoning capabilities of LLMs in themselves to generate more effective training signals, I think this is really promising.
I agree.
And, especially as we kind of look ahead to the future and, potentially facing more and more challenges related to the availability of high quality data.
For sure.
This research is really, it forces us to rethink some fundamental assumptions about how we train these models.
Yeah.
Like what happens when our models learn, not just from the text itself, but from, a learned model of the reasoning that might have produced it. How might that change our whole approach to pre-training and unlock totally new capabilities?
Yeah.
Especially as we're, navigating this future with potentially much more constrained access to the kind of data that we would ideally like to have.
Yeah, it's a really interesting question to consider.
It is, yeah. And what are the potential, both positive and negative of models developing and learning from their own internal thought processes at scale? I mean, it's kind of a mind-bending idea to wrap your head around.
Absolutely.
So for those listening who are, eager to kind of dive into the nitty-gritty technical details of this work.
Yeah, we definitely encourage you to read the full paper. There's a link in the abstract. And the researchers have also made their code and data publicly available on GitHub. You can find that link in the abstract as well.
Awesome.
This is definitely a space to watch closely, and we encourage, the entire AI research community to engage with and build upon this exciting work.
Yeah, absolutely. All right, well, thanks for joining me on the deep dive today.
Thanks for having me.
And we'll see you next time.
See ya!